Yes, we can start.
We can even start because
we can start. Yes, yeah, it's okay. Yeah, well, we'll start slowly. Yes, 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 good. Okay. Yes, yeah, let's do
that. Yeah, hi everyone. Yeah, welcome to this special EECS Physics Colloquium. I'm Umesh Vazirani from Computer Science. So this is probably the first of hopefully many such collaborations between CS and physics, especially given all the ties that we have now, with the Challenge Institute for Quantum Computing and the Quantum Systems Accelerator. So there's all this activity on campus in quantum computing. So I'm really excited that Misha is visiting us today from Harvard. Misha is, I think maybe you've all heard about this wonderful breakthrough that he's going to speak about. Just a few words about Misha. He's I think he's quite an he's an extraordinary kind of researcher in quantum computing, in the sense that he's both a theorist and an experimentalist, and his approach to quantum computing sort of encapsulates both these directions. So back in 2018, there was a panel that we had organized at the Simons Institute, where we invited some of the the panelists were the top sort of prospects for quantum processors, superconducting qubits. There was John Martinez, there was ion traps, and Misha at that time was just getting into creating these neutral atom arrays. And I remember at that time saying, thinking and also saying that I was irrationally exuberant about Misha's approach, because it seemed to me, it seemed, for a theorist, it seemed like, well, this really had prospects for scaling. And more recently, when I heard Misha speak at QSIM earlier this summer about precursors to what he's going to speak about, I was doubly irrationally exuberant about what he had to speak about. So Misha is I believe he's a distinguished university professor at Harvard. He's the co-director of the Harvard Quantum Initiative. He's a member of various fellow of various societies and highly decorated in awards. But the thing that I'd really like to mention about Misha is that he's been extremely successful in collecting a bunch of very, very talented postdocs and graduate students around him who collaborate both in theory and experiment, and with absolutely amazing results. So please join me in welcoming Misha.
So thank you so much, Umesh, for a very kind introduction. I hope my talk will live up to these expectations, but it's a great pleasure to be here, and I doubly thank Umesh for insisting that I actually make it here. So my talk today will focus on kind of building quantum computers, quantum machines, and most of you, of course, know about this exciting frontier, which one can view it as a kind of quest for controlling a quantum world, in which we're isolating and controlling some simple quantum objects and then build more and more complex systems from them. And so with these systems, we of course would like to explore new science, and usually this is a new physics. We've engineered many body systems, like creating and probing new entangled states of matter, but also we would like to start using them to actually explore new applications and perhaps the most important one is building quantum computers, quantum information processing. So before we start kind of going into the details, I would like to say maybe two things which maybe for this audience are kind of obvious, but they are not maybe obvious to everyone, is that despite of all of the excitement in this field, I think we need to acknowledge two facts. One is that at this point we do not know if and how we can build truly large-scale quantum systems, like large-scale quantum processors. And even more shockingly, even we want to build one, we don't really know how we can use them to achieve, to do something useful. I mean, we have some ideas, and some of them are profound, but in all honesty, we don't know the full potential of these quantum computers and quantum systems. And one of the things which I like to kind of to mention is that like one way to understand why quantum computers, big quantum computers, are hard to build is that in order to do it, we have to fight two contradictory forces of nature. So one of them is kind of the trend or a force of controllability, because we really need to basically isolate and control, quantum systems basically at a single quantum level. And another one is a force of scalability. We need to have, a large number of these, qubits, and they should be highly entangled, highly scrambled to execute useful algorithms. And these two forces are in contradiction in many areas of human activities. So, for example, like if you take, a big number of smart PhD physicists and put them in a single organization, by definition, this organization will be very hard to manage. So, but in quantum mechanics, these two forces really collide in a way how, and manifests itself, in a kind of dramatic way, in a sense that, all objects around us are in principle, consists of quantum particles, atoms and electrons, which we know obey the rules of quantum mechanics, but they're, all of these objects kind of in a macroscopic world, they're eminently classical, right? And that's kind of, this kind of indicates, one reason why quantum computers are very hard to build. So we would like to build large superpositions of qubit registers, and keep them quantum mechanical. So nevertheless, despite of these challenges, this is actually exciting time in the field, in that there are kind of now a number of systems which can assemble and control something on the order of, a couple of hundred of the qubits, and, one can start exploring these systems to, for example, execute tasks beyond what modern classical computers can do. But maybe even more importantly, we learn from these experiments, we learn how to build bigger and perhaps better quantum machines, and also start addressing this kind of algorithm and application challenge. Start figuring out what they can be used for. And in some way you can kind of call this, time now which we live in is a kind of an era of quantum discovery, where we can, start building systems which are already, complex and, programmable and quantum mechanical enough that we can really, start exploring things which you cannot easily, calculate with, classical computers. So one way how all of these kind of challenges manifest at a practical level is basically can be summarized by thinking about what limits our ability to execute large, useful algorithms at scale. And kind of in some surprising way, this actually is not a number of qubits. So in fact, right now, as I already indicated, there are several systems which actually operate, on hundreds of qubits. And in fact, as you will see later on my talk, it's kind of very clear that we can, start working with systems with, thousands or even maybe tens of thousands of qubits. The real issue is that, what we need to do is by, working with the systems, we need to start basically execute more and more quantum operations. And in fact, these operations usually, have errors. And what this means is that past certain threshold, past certain number of steps, you basically, start making so many errors that your output of your computation is basically kind of completely useless, And that's kind of, maybe in a practical way how like how these quantum computers manifest the fact that, once you have a large and complex enough system, this system essentially become classical. So this is something that people early on in the kind of in the field noticed, and basically for this reason, kind of very early on, people recognized that these errors in quantum operation is really a fundamental issue, and for this reason, people thought, okay, this quantum computing is a very nice kind of, conceptual exercise, but it will be very hard, if basically completely impossible, to build useful quantum machine. And then in the middle of the 90s, there was a big breakthrough, and this is the idea of quantum error correction. It was a big theoretical breakthrough. And the idea here was to basically use redundancy, kind of similar to the way how classical computers can use redundant encoding. For example, if you want to encode 0 and protect it, instead of just 1 0, you can encode it in 3 copies. And that way, for example, if 1 0 flips into 1, you can just by doing a majority vote, you can figure that error has occurred and correct it. So the ingenuity of the quantum error correction, was that initially it was really not clear at all how to generalize this, classical, error correcting code to quantum case, and it's for 2 reasons. So first off, there is no cloning theorem, so basically which says that we cannot duplicate quantum information, and second, normally, if you make a measurement, you collapse the quantum state, and this basically means that, like, you cannot just follow this, very simple procedure. Nevertheless, it turns out that quantum error correction is possible. And the idea here is that you can basically use entanglement to store information non-locally among several physical qubits, and this kind of non-local storage allows you to measure something which is called stabilizers, basically make some measurements which do not reveal what qubit you encode in this, but can reveal the presence of the local errors. And basically through this kind of non-local storage, essentially by being delocalized, logical degree of freedom becomes hard to accidentally manipulate. That is to say, if one of these physical qubit flips, you can basically use a stabilizer measurement to figure it out, without destroying the quantum information which was stored in this kind of delocalized superposition. So this, as I already mentioned, the mere fact that, you can actually do quantum error correction in principle is actually kind of an amazing discovery. And, it's thanks to Peter Shor and Andrew Steen and John Preskill and Alexei Kitaev. So here is kind of one example, and this is perhaps, one of the most famous example now is so-called toric or surface code. So basically, like you can view this, toric or surface code as basically in some way a product of 2 classical repetition codes, and basically 2 directions on this kind of lattice, and basically, along one direction, if you, for example, flip all of these, qubits, you basically make a bit flip. So basically, take all zeros and flip them all into ones, like in this classical code which I indicated. So along the other direction, you basically make a flips in different bases, so you apply all kind of X operators. But it turns out that, in this code, you can do this so-called stabilizer measurements, which are basically checks of products of local Z and kind of X operators in such a way that if, for example, one qubit flips, then you can actually detect its presence. So it actually will, flip 2 of these nearby kind of stabilizers, and then you can locate this error and correct it. And basically, here, if you make this lattice larger, what you see is that, you need to make, a lot of errors, to basically destroy your logical operators. So what it means is that, by making this lattice larger, you can increase the protection, provided that the probability of error is sufficiently small. So, and that's kind of related to something which is called threshold behavior. So basically, if the probability of error is sufficiently small, then basically by increasing the lattice size, it's called distance here, it's a linear dimension, you can basically, suppress your error in kind of almost arbitrary way. So this approach is an example which offers realistic route towards extremely small errors, and it was this theoretical breakthrough of this quantum error correction which really caused the field of quantum computing to take off. And most of the people believe that eventually we'll need to switch to performing algorithms from physical to basically logical qubits. But already at this time in kind of 1990s, and actually maybe this is something that many of you don't know, so even when these kind of ideas came out, still there was quite a bit of skepticism. And in fact, some of the criticism came, from, at the time, leading physicists working in the quantum physics. So Serge Haroche, as you might know, has actually got a Nobel Prize for pioneering work in designing, in making, basically big quantum superpositions. And basically, they published an article in Physics Today. Actually, I learned last week that apparently they tried other people to sign. So, for example, they asked Peter Zoller and Ignacio Chirac to sign this article, and both of them refused, So, but kind of this argument, but what's kind of interesting, this argument that, they put forward was actually not wrong. So they basically said, look, so what we need to do to build a quantum computer is to build a kind of a big Schrödinger cat. And you guys are proposing to do error correction by building smaller Schrödinger cats to protect, bigger Schrödinger cats, you must be kidding, because, at the time, people could entangle maybe, 2-3 atoms at most, and this was done by these guys. And, this is actually extremely challenging. So, in fact, they said that, therefore, we think it's fair to say that unless some unforeseen new physics is discovered, the implementation of error correcting codes will become exceedingly difficult as soon as one has to deal with more than a few gates. What's ironic is that many of the techniques, okay, so first off, let me say that these people were not wrong, so, and as a matter of fact, up to now, logical qubits have been very hard to build and control, and in fact, some, pioneering recent work demonstrated, like 1 or 2 very small logical qubits and basically 1 logical gate operations. But what's also ironic is that actually a lot of the techniques which we are now using to actually create and control these logical qubits have been pioneered by these guys. Both cavity QED and, as you will see, Rydberg atoms, which we are using, have really been extensively developed by Serge and co-workers. Okay, so what I'll do today, I'll tell you about, our approach to basically exploring this quantum error correction frontier. And so I will tell you briefly about the physical platform we will be using, and this will be atoms trapped in optical tweezers. I will tell you how we actually assemble these quantum systems, how we control it, and then I will move on to describe, our first kind of realization of the first, we call it first generation logical processor, and what kind of experiments we can do with that. So, to begin with, this is how all of our experiments start. So we will use cold neutral atoms to build quantum systems. And all of these experiments start with basically a blob of cold atoms, which contain typically, a few million of the neutral atoms, which are virtually at a standstill. They are moving very, very slowly. So this is an image of something which is called magneto-optical trap. And actually, so what it really means is that, the source of cold identical neutral atoms, qubits, are essentially unlimited. So if we can control them all, we can, have easily, 10 or 100 million of the qubits. But the key challenge is to really, control them. So basically, you could say, in the same spirit, here in this room, there are a lot of atoms and molecules. If we could track each of them, right, and control them, it could be a big quantum computer, but, that's clearly not trivial. So, motivated by that, a few years ago, we started kind of exploring a new approach to building scalable quantum systems, in which what we do is we use tightly focused laser beams of light to basically grab and hold individual atoms. And so basically we focus these lasers so tightly that each of these beam can basically attract to the point of the maximal intensity and hold at most one atom. So the two atoms just get ejected from that. And so basically this beam of light is often called optical tweezer for this reason. But we don't just usually start with one of these traps. We now start with thousands of traps and basically try to fill them all with atoms. And usually, what happens as we try to do it, we end up with this, atom array, which is partially filled. There is like a lot of disorder, there is entropy. So to get rid of this entropy, what we literally do, we take a picture of these atoms, figure out which traps are full and which are empty, and then basically, either eliminate the empty trap or just rearrange the rest of the atoms or both. So we can, for example, get rid of these traps and rearrange it in the desired configuration. And then what we, at this point, we end up with essentially a classical system of identical atoms, situated typically a few micrometers away from each other. So at this point, the atoms don't tunnel, they don't interact. And to make them interact, what we do, we actually excite them into the states with large principal quantum number, so-called Rydberg states, where they start feeling each other as present. And that's how we do, for example, quantum logic. And so this is our joint effort, which now runs for almost a decade. It's collaboration between my group, the group of Markus Greiner, my colleague at Harvard, and the group of Vladan Vuletic at MIT. So just few more words about this excitation into Rydberg states. The reason why we like Rydberg states is because they combine long lifetimes and strong interaction. So in fact, if you excite the atom into the state with principal quantum number 100, the van der Waals interaction between these atoms is 14 orders of magnitude stronger than the van der Waals interaction between ground state atoms. So 14 orders of magnitude is a big number, and we can make good use of that. So in addition, these Rydberg atoms also have relatively long lifetime, and what it enables us to do is to use these techniques, which is called Rydberg blockade. So the idea is actually very simple. So imagine we have these atoms which are sitting far away from each other, and we drive these atoms resonantly into the excited state. So what will happen in this case, the atoms will just undergo independent Rabi oscillations. But if we now bring these atoms closer together, at some point these interactions will take off. And if you still try to excite these atoms, both resonantly, you will not be able to do it. You will be able to excite one atom or another, but not both. And this is the essence of this Rydberg blockade. It means simultaneous excitation is blocked at distances smaller than is blockade radius. And actually it turns out it's a very good mechanism to entangle atoms or do quantum logic because it's very robust. It's insensitive at this point to the exact position of this atom. It also is insensitive to motion. In some way, this is a kind of an approach to make this interaction almost digital. So it's either off if the atoms are far away, or it's on and it's basically almost infinite if the atoms are close to each other. So this is a feature which we will use extensively in what I will show you in the following. So this very robustness and digital character of interaction is one of the key ingredients to what I'm about to tell you. So altogether, so what we'll be doing and what follows is shown here. So we'll start basically with a bunch of atoms which are sort of randomly placed in these different traps, and then we will rearrange them into some kind of registers. This is, by the way, these are pictures of single atoms, real single atoms in our vacuum chamber. And then what we'll do, we will send laser pulses to change the internal states, change the spin states, sometimes excite them to the Rydberg states. And then afterwards, after this evolution, we will measure atoms again in a kind of state-dependent way. So we will, for example, image the atoms in one state, and kind of keep them dark in the other, and that way we can actually find out what the result of this computation is. So I should say right away, this is now actually a very exciting field. We've actually several experiments under construction around the world, and at least 6 companies trying to commercialize this technology. And actually, there is kind of now a wide variety of different atoms, even molecules are being explored. And in fact, some of these experiments become quite exotic. So this is, for example, a 2-species array in a Hannes Bernian lab in Chicago. There are 2 atoms, I think rubidium and cesium here, which can be independently controlled and imaged. And actually, this is really an exciting frontier because it kind of bridges, subjects from many body dynamics to quantum computing to quantum metrology. It's actually complementary to another exciting research direction involving optical lattices. It's a different way to create potential. So in many of these experiments, the key element which is being used to trap the atoms is this device called special light modulator. It's actually the same device which is used to project this, from the projector to project these slides here. So it's essentially a computer-generated hologram which we can use to, for example, deflect the laser beam, incoming laser beam in different directions, or we can create this kind of, more advanced hologram which actually would project essentially would create a 2-dimensional array of these light beams, which if we focus into the vacuum chamber could create this, extremely homogeneous large arrays of optical traps. So this special light modulator is an amazing tool, but it has one drawback. It's actually slow. So in order to move atoms around, what we use another tool. We use something which is called acousto-optic deflector. So it's a crystal in which if you set the acoustic wave, this acoustic wave would deflect the laser beam by a certain angle. And actually, we use 2. It's a device which is used sometimes. You can still see it in a supermarket as a kind of barcode scanner. That's the same kind of idea there. We use in our experiments this device extensively. In fact, here we use 2 acousto-optic deflectors. One of them will be used to move atoms in horizontal direction, and another one will be used to move them in a vertical direction. So as you will see, this acousto-optic deflector is actually very important, and we'll use it now for different purposes. And in fact, we have now 2 sets of optical deflectors in our experiments, and actually introducing a third as we speak. So it's all computer controlled, and this actually gives rise to already a 3rd generation of our atom array system. At Harvard, this 3rd generation is basically specifically optimized to do a few things. First off, we can now work with larger systems. We can now work with systems over thousands of atoms and reliably create arrays of up to about like maybe 600 or so atoms. So we also have high fidelities to control the system, and we also have a number of advanced control tools, which I will describe in a second. And with systems like this, I must say, last couple of years have been a lot of fun. We were able to explore very different directions. So we were able to study, for example, complex phases of matter, study non-equilibrium dynamics, probe topological spin liquids. It's something which, people thought about in condensed matter physics for 50 years. And, this was the first experimental demonstration. So we also are kind of starting to explore various types of quantum algorithms like combinatorial optimization. And actually, we have now more than one atom array in a kind of our broader Cambridge, Harvard, MIT community. In fact, one of the machines is now a startup company, Quora Computing, across the river. It has been available since about a year now publicly, so you can publicly access and kind of, and program it. So all of these experiments, they basically involve some sort of analog, sometimes a combined analog and digital dynamics. So I'm not going to talk about this today, but today I will really focus, on digital processes and in particular on this idea of quantum error correction. The key innovation for that was a work which we have done about a year ago, 1.5 years ago, in which we demonstrated what we call reconfigurable quantum architecture. So in this approach, what we do, we encode a qubit in a long-lived hyperfine state. It's basically a spin state, sometimes electron, sometimes nucleus spin of an atom. And in this hyperfine state, the qubit can live for a very long time. It's basically lifetime is limited by vacuum, which is, in our case is, some maybe tens of seconds, but it can be much longer. But what we realize, and this we knew, for a long time, but what we realize is that not only we can store qubit in this atom, we can also move this qubit around by just shifting the position of optical tweezer, basically without destroying quantum information. And what this allows one to do is allows one to build a kind of a system where the connectivity of the underlying architecture is basically like a living organism. So effectively what we'll do is we'll position atoms in some way and then, excite them, entangle them, do a few gate operations. Then we will shift the atoms, some subset of atoms, change the connectivity, again apply a few gates, then shift it again. So basically, kind of as the computation proceeds, we can basically, evolve how the atoms are connected, and this turns out to be very powerful for two reasons. So first off, it of course creates a non-local connectivity, and second, it enables one to really efficiently control these atoms classically in a highly parallel way. And this is the features which we are going to be using. So in fact, one could actually use this kind of reconfigurable architecture for many different directions and applications. One of them, one could actually study entanglement dynamics, like for example making two copy measurements. One can also use it, kind of combine it with many body physics. We're also starting to explore kind of potential applications to quantum chemistry simulation. In fact, this is a collaboration with Martin Head-Gordon group here in chemistry. So we just I think we have a paper on arXiv since about a week. So there's also similar ideas can be applied to kind of create dynamics of topological matter, lattice gauge theory. So there are some much more exotic ideas to, for example, utilize not just spin degrees of freedom, but also motional, like fermionic degrees of freedom. And I think these are all super exciting directions. And the only thing is that at the end of the day, all of these things fundamentally will be limited by errors, so, and, it turns out that this reconfigurable architecture is also very naturally suited to correct the errors. So as an example, let's go back to this kind of toric code, to this example that I gave. So in this toric code, as already indicated, we need to have some, arrays of physical qubits which will protect, which will store the information. And then we also need to add these kind of ancillas which will do the so-called stabilizer measurements. So they will check if the error has occurred or not. And so original toric code was actually obviously on a torus, and you would say, well, it's actually hard for us to create this, kind of torus on a two-dimensional geometry, but actually it turns out that it's possible with reconfigurable architecture. So here is a movie showing actually a circuit. So this again, these are real atoms moving. So these are ancilla atoms which move around to basically make these, checks. And actually one of these moves is this highly non-local move, moving all the way around, allowing us to effectively create a torus. And then these ancillas are moved to this kind of ancillary doubt zone. So two important things. So first off, this circuit, this entire circuit, which actually encodes two logical qubits, one logical qubit going this way, another one going this way, actually is specified by just two control voltages. One corresponding to atoms moving vertically, and another one, atoms corresponding moving horizontally. And so this actually allows us to basically, have super parallel, very efficient control over many physical qubits, with the number of controls which scales the number of logical qubits. So that's kind of a key to the approach which I will describe. So recently we have actually made a few important technical upgrades. So first off, we improved the fidelity of our entangling operations, which is now below the threshold, for example, for this surface code. So we also have now an ability to make fully programmable kind of parallel single qubit gates. And again, what we do here, we use these two acousto-optic deflectors to project the patterns on these various on these qubits, and it's actually the fidelity of this is quite high. And then finally, we now are able to do readout of qubits in the middle of the circuit. So the way how we do it in our approach is just by grabbing some qubits, moving them into the readout zone, and just reading them out, and then having a fast FPGA kind of circuit to execute, to make a calculation, and basically produce a signal with which we can control, flip the qubits in the storage zone. So all of these, things, I should say, kind of indicates that there is actually a remarkable kind of progress in this neutral atom community over just last, year or so. So, for example, this mid-circuit readout, for a long time, people say, oh, it will be very hard, impossible to do it with neutral atoms. Actually, by now, there are, like maybe 4 or 5 different approaches to do it. And actually, one of the pioneering work was done here by Dan's group in Berkeley. Okay, so all of these ingredients, when combined together, allow us to think and envision the first quantum processor which actually operates on logical qubits. The key idea here is, again, this very efficient control. And to kind of illustrate it now, maybe in more specific context, I would like to actually consider now quantum operation a logic gate between 2 logical qubits. So because the quantum information is delocalized over each of these logical qubits, actually making this quantum operation, this entangling gate, in general is quite hard. So basically, you need to make sure that each of the physical qubits from this block somehow goes around and feels the presence of each of the physical qubits from this block. So it's kind of, you can think about it in different ways. So for example, if you're thinking about like anyons, for example, in this kind of topological code, you could say you need to braid an anyon, one around another. So if you think about more like a kind of conventional thing, you should say, well, you need to swap these qubits, in such a way that they all kind of feel each other's presence. So this is obviously quite hard. And moreover, if you start doing it this way, and that's, for example, the idea of something like lattice surgery. So it turns out to make it in a fault-tolerant way, so you need to make a lot of the rounds of error correction. So you need to make, generally, you need to make D rounds, where D is a code distance, a linear dimension of this code of error correction. But actually, there is a kind of an old, kind of Slavic, saying that everything new is well forgotten old. So actually, very early on in the kind of quantum error correction era, people like, John Preskill, recognized that there is another way of doing it, and this is the so-called transversal CNOT. So in this transversal CNOT, you need to directly interact the localized degrees of freedom. So in particular, in our approach, what we can do, we can just pick up one of these qubits, logical qubits, bring on the top of each other, and then basically make an entangling operation between pairs of physical qubits which are sitting on the top of each other. So this is an example of this so-called transversal, 2-qubit gates, transversal CNOT. So, but then bringing them apart, you basically end up with one step with the entangled qubits, with the gate between the qubits. So there are a few features of this transversal CNOT which are very important. So first off, these transversal gates are inherently fault tolerant, and the reason is that errors don't spread between the blocks. So in general, these D rounds of error corrections are not required. So moreover, by moving these qubits around, you immediately implement these long-range direct connections between potentially distant logical qubits, and this also can be very important for large-scale algorithms. Most importantly, we can now think about these logical qubits as like one big atom. We don't need to think about individual constituents, in this. So we really operate on that as one big block, and here the kind of the combination of these transversal operations and this optical, parallelism is like super important. Okay, let me give you a couple of examples what we can do with these operations. The first one is a logical CNOT with a surface code. So basically, what we'll do is we'll prepare one of the qubits in a plus state, another one in 0, and then just, basically make a control node operations to create a Bell state. So the way how we do it, we start with the surface code is basically like a toric code, but just on the surface. So what we'll do is we'll basically prepare 2 code blocks. In one case we'll measure Z stabilizer, another case measure X stabilizers. And then what we'll do after the preparation, we basically will just bring this 2 codes together, entangle them, and then basically separate them and just check if the state is entangled or not. So this is kind of the smallest possible, code with distance equals to 3. But the key of this quantum error correction is that, provided you are below threshold, the operation should improve with the system size, with the code distance, and this was actually kind of already attempted earlier this year with the single qubits. So Google made experiments with 3 and 5 distance code. So what we can try to do, we can try to increase our distance to 5, but we can also grow it to 7. And now instead of just doing single qubit operation, we'll try to really entangle them. Okay, let's see how it works. So first off, for the distance 7, we can measure the qubits in kind of X and Z basis, and we see clearly that these qubits are entangled. And what's more important, as we now look at the scaling with the code distance, we clearly see that fidelity improves, the error decreases as we increase the our code distance, our encoding block. So that's a key, basically, feature of the quantum error correction. By growing the system size under certain conditions, by creating more entanglement, the system becomes more robust. Now, there are various caveats about this. So first off, to actually see this improvement, we found that what we need to do is, after this operation, we should not encode qubits individually, but we should we should not decode qubits individually. We should decode them jointly, and that's actually connected to the fact that this during the logical operations, the errors can propagate. And actually this correlated decoding turns out to be a very important feature. So one other important caveat is that, here we just make one round of error correction. So, and, basically decode immediately. So, things could be a little bit different, if you make multiple rounds of this, error extraction. But nevertheless, despite of that, it's very clear that, entanglement and quantum operations with logical qubits here improve with the code distance. And, moreover, already from these relatively simple experiments, we really kind of discovered that there are certain things which we have to do, which people really have not thought about. So this correlated decoding, if you think about for a second, of course we need to do it, but it's actually kind of, there was like 1 or 2 papers about it. It's actually really very, very, very interesting. So one thing, and one reason that, for example, that here decoding is very important is that actually when we prepare these states for this distance 5 and distance 7 codes, actually our preparation is technically not fault tolerant. So, but we can also work with other codes to do fault tolerant preparation. So here is an example of another famous code, which is a color code. It's kind of very similar to the surface code, just a little bit kind of, different from this. So basically what we do here is we prepare 2 color codes non-fault tolerantly. This is a circuit, how to do it. And then what we can do, we can use one of these color codes to check if the other one has been prepared properly. So that's actually something which is called Steen error correction, also something from the very early days of the error correction literature. So basically what we'll do is we'll do a Hadamard, on this one of these logical qubits. Then, we'll kind of execute basically, C0 or C-phase operation, and then basically afterwards, measure this state of one of these qubits. So basically it's kind of corresponds to like a logical Ramsey experiment, if you want. So basically in this case, if you measure and this qubit is in a 0 state, and with high probability this guy should be in a 0 state. But if you see that it's 1, then it's actually you made an error. And so with this procedure, so we actually can prepare our code blocks, better than we can prepare our physical qubits, and actually even better than we can do quantum logic. So in this case, basically our spam error on logical spam error is around 0.01%. And while experiments like this has been done previously, in particular by the Continuum group with ions, we can again leverage this high parallelism here because we don't need to do it on just two qubits, one pair at a time. We can do it on multiple pairs. In fact, these are the results, which are average over 4 pairs. And once we have these, 4 logical qubits prepared fault tolerantly, we can start using them for algorithms. And so one of the simplest algorithms which we can do, we can prepare a small ket, the so-called GAG states, by basically, preparing, these 4 qubits fault tolerantly, and then just basically doing some gates between them to entangle them. And actually, in this case, we see that now we can, by doing various decoding tricks, that in some cases, we have basically close to unit fidelity, and moreover, we can also do things like tomography, So, for example, this is a measurement of all 81 logical bases where we extract, all kind of, elements of the density matrix. But moreover, one could also start combining these things with, for example, like mid-circuit readout. At this point, you can also think about doing teleportation of the logical qubits. So here's, for example, we prepare a 3-qubit GAG state, and then we measure the middle one, and then basically, depending on the measurement, we basically can output a signal which, will allow us to apply a phase to these other qubits to basically create, for example, like a deterministic kind of a Bell state. So, and this circuit is implemented by just taking one of these entangled qubits to a readout zone, reading it out, and implementing this, feed-forward signal. So what I hope you already see is that some architecture of something which really looks like a processor is emerging. So we have this, entangling zone, storage zone, and kind of readout zone, and can move things around to really execute more and more complex circuits. And this is really, creates an exciting openings to really exploring this kind of early error-corrected algorithms with logical qubits. So I'd like to finish by just giving one example, of this kind of exploration. And this example really hopefully shows that this quantum error correction is really exciting scientific and not just engineering frontier. And in particular, in these early days, what you really want to do is you want to think about, the algorithms you want to execute and co-design it with the optimized error correcting codes and with some specific hardware capabilities. To show this, I will look at the example of non-Clifford operation, which is arguably kind of the hardest thing which one can do with the logical qubit. So in fact, the reason is the following. So these Clifford circuits, like applying X, Z, Hadamard, it turns out can be simulated classically simply because you can just look at operator propagation through the circuit and just follow how the operators evolve. But once you add non-Clifford operation, this is no longer possible, and that's the reason why these non-Clifford operations often are called quantum magic. So, and this quantum magic, however, is very hard to generate in this kind of error-corrected circuit. So there are various techniques which are, being explored, which are generally very costly. So the question we asked is, if we don't want to be very general, but can we somehow find ways to efficiently generate this magic? And one example how we can do it is by instead of 2-dimensional codes, working with 3-dimensional codes. So it turns out that for 2-dimensional codes, all transversal operations are Clifford, but this is no longer the case if you go to 3-dimensional codes. So the smallest interesting color code is a 3-dimensional code, which is 832 code. It actually has 8 physical qubits, on the here at the kind of not edges, how they are called, the corners of the cube, and actually this color code encodes 3 logical qubits, and actually it has code distance 2. What it means is that it's actually error correcting for 1 qubit. It's actually only error detecting for one other qubit for one other error it's error correcting for one type of error and error detecting for another error. So basically, these kind of logical qubits here are basically, kind of can be defined as kind of, surfaces and edges of this, of these cubes. And the kind of beauty here is that you can actually do non-Clifford operations. In particular, you can do CCZ operation, which is non-Clifford operations, by just applying single qubit, pi over 8 rotations on some, individual, qubits within this kind of code blocks. And then, in addition, of course, we can do transversal CNOT. We can deploy all of this machinery which we have enjoyed so far. Okay, so with all of that, what we'll do is we'll do the following. So we will prepare logical states plus, and then apply parallel CC and CZ operations within a block, then apply parallel interblock CNOT operations, and then repeat this multiple times, and then eventually measure in X basis. So it's actually turns out that this circuit is an example of scrambling circuit, so it actually generates entanglement very efficiently. And what we will be doing here, basically, we'll be making hypercubes of logical qubits. So in fact, the most advanced kind of algorithm we'll be making 4-dimensional hypercube of logical qubits, which actually corresponds to 7-dimensional hypercube of physical qubits. So, and this is like the kind of things which we will be doing. So, basically, it's actually fun, So, but actually, it also turns out to be kind of very important, because this circuit maps into something which is called instantaneous quantum polynomial circuit. So it's actually a scrambling circuit which is classically hard to simulate for large qubit numbers. It's actually one of the early examples of this quantum, so-called quantum supremacy circuit. And basically the output of the circuit will be kind of a random pattern of basically, kind of, strings, of the qubit strings. And, this means that, basically what we will be doing is we'll be doing sampling. So here is, an example with relatively small circuit, which actually is relatively easy to simulate. This is just, 12 logical qubits. And so if we executed it perfectly, so theory predicts that we should see, kind of probabilities, depending on logical bit strings, behaving in certain way. So it's basically an example of this speckle pattern. So if we don't do any kind of, error correction or, error detection, what we see is that something, well, maybe there is this big peak which kind of reminds that, but, it's really very clear to see how these two resemble. But now we actually start, introducing this error correction and error detection. So we basically start looking at samples where more and more stabilizers, behave properly, and just throwing the samples where stabilizers show that we have errors. And what you see very beautifully is that there is this like a shadow of this perfect distribution is emerging. So this red curve in particular, really very closely resembles what we should be expecting in theory. So there is way to characterize it by, for example, using something like XCB. It's basically a fidelity, an overlap between these two circuits, which actually shows that if we do sufficient number of error detection, basically fidelity is quite high. It's basically, approaching, within like 30% of the unity. So basically what it shows is the result of error detection are very close to the ideal state, but actually I would like to give you one more kind of little bit more technical slide to show you that these error corrected circuits are actually special. So they are very different from what we used to think about this kind of normal basically physical circuits. And in order to do that, what I will do, I will just try to zoom in. So this actually is data from supplementary information of our paper. So basically, okay, I showed you that basically at this kind of high level for this large for the probable strings, we have, kind of our error detected, error corrected, result resembles, very much the theoretical distribution. But now let's zoom in, on this kind of smaller features, What you see is that even in the smaller features, there is a very close resemblance. Even if we look at at something which almost looks like noise, there is an amazing, coincidence. So basically, what it really shows is that these error-corrected circuits are very, very different. They basically acquire this digital character. So you can, for example, like, things like miscalibration errors, they're all corrected, once, they applied. It's actually something very special, and actually I find it amazing. Okay, so with all of that, what we can do now, we can scale up the system, and we've done these experiments up to the 48 logical qubits, and what we see is that, for all of these things, if we do some error detection, our results improve. So this is actually the most advanced circuit. These are circuit for logical qubits, that we have made, and basically what we see is that, for this logical circuit, that our results, significantly improve, if we do this error detection. In fact, these results are at least an order, actually more than 1 to 2 orders of magnitude better than, like our best possible, physical fidelity, and it's also roughly an order of magnitude higher than, like, comparable physical circuits which have been made. So here is a movie. Again, these are pictures of single atoms. So this is exactly what we are doing the experiment. So this circle indicates that we are doing the gate. So basically what we see here is we are building, hierarchically larger and larger entanglement. We are building these hypercubes, So what we see here, we run out of storage, so we have to put some of them in the storage zone, and now we entangle the second one, and entangle even more, and then in the final step we will entangle them all together. So I think by some measures, by many measures, this is one of the most complex circuits which have been executed on a quantum computer up to date with actually a meaningful outcome. And I think this actually is really is very cool, very special. Okay, so we actually don't want to stop from there. This sampling task is kind of boring, because it's not like, it's not really producing anything useful. So we also starting to wonder, can we use these logical qubits to actually do some useful, for example, quantum simulations? And here we can probe the fact that these hypercubes circuits are the so-called fast scramblers. So the way how we can measure the scrambling is by using the so-called two-copy measurement. So it's actually, this two-copy measurement is a very powerful tool, which, for example, you can use to measure entanglement entropy. So here is a circuit, where we create 2 copies of 12 logical qubits, and then we make a Bell measurement by applying transversal CNOT between them. And so this is an example. So this actually is the result. And finally, one of my colleagues, Markus Greiner, who is actually kind of an expert in quantum simulations, when he saw it, he finally got very excited, So, and basically, what you see here is something which is kind of like a page curve, So, but, basically, what we do here is, we basically look at the entanglement, logical entanglement entropy as a function of subsystem size. And basically, for for the case where you have, a lot of errors, what should happen is that this, entanglement entropy should just grow with the system size. However, if the global state is pure, then what should happen is that, the entanglement entropy should go up to about half of the system, and then should actually drop, because the global state is pure. And this is exactly what we see as we start to apply this error detection. So this indicates that these logical qubits can actually be useful already now for probing physics of this entangled complex system. And I think this is really an exciting kind of opportunity for this early kind of fault-tolerant processor. So I want to finish up by mentioning kind of a road ahead. So I think there are very bright prospects for kind of scaling up the systems of the type we are discussing. So I would say it's very clear for us how to go to systems with tens of thousands of physical qubits, and maybe with a little bit improving kind of error rates to maybe 0.1% level, which again, we believe is very kind of imminent with current technology. There is a path to like building devices with something like about 100, logical qubits, and maybe the error rate of maybe 10 to the 5, minus 5, 10 to the minus 6. One of the things which we'll need to do right now, these experiments work in a kind of pulsed mode. So we prepare these arrays we do experiments, and then we stop, we prepare another array. So there are ways in atomic physics, we know, they are very well known how to actually turn it into a continuous operation. It just needs to be kind of integrated. But even beyond that, I think there are many new avenues how one could envision then scaling beyond these 100 logical qubits devices. So first off, I think there is very exciting new directions now starting being explored involving novel encoding. So it's very clear, for example, that things like surface code is not the best approach. There is this family, for example, of quantum LDPC code, which allow much denser coding. So on the atomic physics side, we should start thinking about, not wasting laser power too much, So for example, maybe combining these tweezer platforms with optical lattices for storage, also with the ideas of connecting modules, for example, using some, cavity arrays or cavity techniques, But with all of that, I think this all potentially could result, in approaches to scale up to, a kind of 1,000 plus logical qubits. So I think this medium scale quantum error correction system will be really a new tool for scientific exploration, and we really hope that with this kind of advances we can really accelerate the path towards larger scale kind of useful quantum computer. I would like to emphasize again that this error correction is a very exciting frontier which actually combines both science, engineering, and applications. So it's not just engineering, as some people say. And I think there are really cool opportunities for both building, using, and kind of exploring this large logical processor. So I think I used up my time here. So I hope I convinced you that this is really kind of an exciting scientific frontier. Maybe there is a little kind of new era starting for kind of early fault tolerance, And with that, I would like to thank, you for your attention, and actually thank in particular the group of amazing graduate students of postdocs. Actually, these experiments have been done in our university lab by a small group of people who are basically compiling this and programming these circuits by hand, but also with contributions of several amazing theorists. So this is what Umesh said. It's kind of, this is an area where basically theory and experiment and engineering should really converge. And actually we also are were greatly helped now by our colleagues at Quera, which actually developed a couple of tools and instruments. And with that, I would like to thank them all and thank you for your attention.
So congratulations on these wonderful results. And I'm thinking about the other types of qubits. They also had large numbers of qubits, but they never achieved true error correction. So what went wrong with the other types of qubits that you corrected?
All right. So this, first off, I'd like to say that, I hope that what this work really, it really just opens a new frontier, and it does not close it. So I think there are certainly, many other approaches which are being pursued, which I definitely believe that should be still pursued. So, and moreover, for example, in doing these experiments and kind of, like over the last couple of years, the progress in this field of neutral atoms accelerated greatly. That's thanks to the amazing neutral atom community, but also we learn a lot from the experiments done with trap ions in particular, but also with superconducting qubits. All that being said, there are a couple of areas in which we have, I would say, like kind of an unfair advantage, And one of them is that, is a kind of maybe very simple to understand. So I don't have my cell phone, but if you think about your cell phone and you think about a processor in your cell phone, so it contains, how many, maybe billions of transistors. Think about how many wires are being used to control this processor. I mean, there are certainly a lot of wires, but not billions. So these optical techniques, these optical multiplexing techniques, which we use to efficiently control logical qubits are very special. So normally, for example, if you have superconducting qubits, each of these superconducting qubits, physical qubits, requires many wires, to correct. In our case, with 1 voltage, after multiplexing, we can address and control basically logical qubits as a kind of building blocks. So that, I would say, is a key to what we have done. There are other things like this reconfigurable architecture. The fact that our qubits are actually atomic clocks, so we don't really need to correct memory errors. We only need to correct errors in these logical operations. All of these things, are very important. But I think with all of that said, I think we are just in the beginning of the journey.
Yeah. So you did not mention fidelity. Now, by the fact that you have achieved the error correction, you have an automatic way of guaranteeing the fidelity. I think in some of the other types of qubits, they don't really know what their fidelity is.
Well, yeah, that is a good question, but this is the one which actually, so like if you know the history of these Rydberg kind of approaches, so these are the ideas we first thought about over 20 years ago. And people started, working with these qubits. But for example, like the fidelities associated with these neutral atom qubits have been actually not as good, or trailing behind both ions and superconducting qubits. And only very recently, through basically, clever, again, scientific innovation and engineering, also improving the sources, we actually, I would say, right now, our kind of fidelities, physical qubit fidelities are on the same level as superconducting and ion traps, but the key is that we can achieve these fidelities in a highly parallel operations, operating on hundreds, for example, of pairs of atoms. And it's very special. Again, it's a parallelism combined with things like fidelities, which enables these things. And like fidelity improvement will never stop. So the better our physical qubit fidelities, the easier will be. The physical qubit fidelity goes to the exponent of the quality of life of graduate students, postdoc, and even PhD researchers. Yeah.
Hi, congratulations for the amazing results. I had a doubt when you saw the 2 distant 3 color codes and you said that you used, so the encoding was non-fault tolerance, but then you use another logical qubit and you use that type of Ramsey logical to, so but the first logical qubit, you didn't use even a flag qubit to prepare fault tolerantly?
Yes, so this is kind of a version of flag fault tolerance.
Yeah.
But it kind of predates these flag ideas, So actually, it's known as, it's an approach which Andrew Steen proposed.
Yeah,
it's called the Steen error correction. So effectively, this is like we use one qubit as a flag to check another.
Yeah, you use the Steen error correction.
Exactly.
But to prepare the first logical qubit, so you have this non-fault tolerance
Exactly,
circuit.
yeah.
You don't.
Yeah, so what this is an essence of this Steen and so on. So you use 2 non-fault tolerant circuit to basically distill 1 fault tolerant qubit.
Okay,
that's the key.
Okay.
Yeah, that's Okay. It's exactly. Yeah.
Congratulations, very nice. I was wondering, at the beginning you mentioned, in terms of useful tasks you're interested in, I know you have some work on metrology with error correction. I wonder if you have any plans to actually execute one of those things on this.
Yeah, that's a great question. So, I would answer is that now all of these kind of old ideas can be tested in a lab, and explored. So, in particular, the application to metrology is a very intriguing one, but there are also clearly some limitations, and so in particular, if you have really fully error-corrected device, your metrology signal is actually a signal you want to measure, right? And, as a result, like if you error correct this signal, then will be no measurement, right? So basically, what I think for this metrology, you really need to design error correcting codes, which will correct, most of the errors, except for the channel in which you actually have your signal. So, and there has been a couple of kind of theoretical proposals, and I think now they can be tested experimentally. You are completely correct. And in fact, people already, I think, like Shimon, thinking about how to use some of these techniques to improve things like clocks, for example. Right?
Yeah, you pointed already out that fidelities are important.
Yeah.
Do you know what limits currently your fidelity and?
Yes. So we actually, we do know. In fact, this is one so early on we had a paper this year when we had demonstrated this 99.5. And in addition to just improving the numbers, for the first time we have actually very good understanding where the errors are coming from. And I would say, kind of in light of that, there is quite clear path to 3 nines. So basically, our leading error is a dephasing error, which is in part due to the T2 star, due to kind of fluctuations of the Rydberg states, and it's kind of related to electric fields and so on. And for example, in some of the other systems which we built, this T2 star is actually much better, But even if it does not change, just by doing gates faster, you can decrease this error significantly. One other kind of, contribution to this, to this T2 star of the Rydberg state comes from light shifts. And this in particular is important if we want to do these operations on many qubits in parallel. And so normally now what we do is we illuminate all qubits from the side. By the beams with holographic techniques, we create flat tops. And basically, right now, this homogeneity of these flat tops is what limits us. So in particular, in this, our previous paper, Nature paper, we have 99.5% where we operated on 60 atoms in parallel. In some of these experiments, we actually operated up to 160 atoms. So for these 160 atoms, we saw some fidelity slightly degrading, So basically, for me, we're just improving a little bit, the speed, using more power, detuning a little bit more from intermediate states. There is no question we can hit 3 nines. The only maybe one, little bit of uncertainty, can we hit, 3 nines and still operate, for example, on hundreds of atoms in parallel? And this is what we're working on. I mean, to be honest, if we just focused on this fidelity rather than doing these experiments, I'm confident we would have 3 nines by now. But, that's for sure, we would need it if we want to scale up. And I think, I would say 3 nines is eminent. Beyond that, we have to see. We don't know what will limit. It would be nice to go beyond,
Do you see any issues with crosstalk?
Very little, So, and I think this is here, this basically, this digital character of the blockade is very important. So, in fact, in our gate fidelity paper, we benchmarked this, and we saw a little bit of cross correlations, which were mostly due to the Rydberg atoms, which actually were leftovers, which we did not de-excite. But for example, when we use atom moving, it requires some time to move atoms. These errors just go away completely. So I think this crosstalk is really negligible here. I mean, if you do it right, But I mean, for example, crosstalk limits again how densely we can pack the atoms, right? I mean, there are some considerations. So basically, maybe to summarize, I think this 3-9 operation is eminent, But we don't want to just do 3 nines. We want to do 3 nines in parallel on maybe a couple hundred atoms. And how to do that? This will require a little bit of work, but these are all classical optical techniques, right? In that sense, it's. I'm very, I'm quite optimistic this will be done actually soon,
Great, thanks, Misha. That's really impressive.
So, actually, can I ask like a very basic question? So, supposing you're doing like multiple rounds of error correction, and you measure a syndrome, and you see some qubits flip, like physical qubit flip.
Yes.
So, I mean, I kind of agree. You can kind of